So far we discussed eutectic transformations and then effect of different cooling rates over the structure of an alloy. That is coring phenomena we discussed. So coring phenomena has to be avoided. So the coring generally can be found in case of castings where non-equilibrium cooling is preferred there. So you will get heterogeneous structure. So chemical composition changes as the point changes. So chemical ingredient exists, chemical gradient exists. So that's why in order to check the hardness or mechanical property of such components or such alloys, so Brinell hardness test is widely recommended because it covers more area of the surface, whereas Rockwell hardness test covers only small portion of the surface. But Brinell hardness test, you can see, we know that it is a 5 mm 10 mm ball. So 10 mm ball is highly recommended where there is a casting structure, so that you can cover more area and you will get more accurate hardness value. So Brinell hardness test, the major advantage is that it can be used or it is widely used where casting components are there. In today's session we will discuss one more type of phase diagram. So this is aluminum silicon system. As you can see here, so two metals completely soluble in liquid state, you can see, but completely insoluble in solid state. So practically, so this particular region doesn't exist. So means there is no solid solution present in aluminum silicon system. So aluminum doesn't dissolve silicon and silicon doesn't dissolve aluminum. So you can see here. So practically, so this region is absent. You can see almost 0% silicon can be dissolved into the aluminum, and similarly silicon dissolved 0% aluminum. So two metals completely soluble in liquid state and completely insoluble in solid state. Now you may wonder what kind of microstructure you will get in this kind of situation. So here no solid solution, so there is no alpha and beta. And you can see, so this diagram is also an eutectic type diagram. So lowest melting point observed is around 577 degrees centigrade. So that is the lowest melting point. So this is an eutectic diagram. So around 12%, around 12.5% silicon. It is the eutectic composition. So this is your eutectic composition, and this is a eutectic temperature. So this is eutectic composition and this is eutectic composition. So this point is eutectic. So that's why you can see melting point of aluminum is around 660 and melting point of silicon is around 1400 degrees centigrade. But lowest melting point is present at around 12.5% silicon. So that's why in casting industry, particularly aluminum castings, so 12.5, around 10 to 12 or 12 to 13% silicon alloys, aluminum silicon alloys are highly preferred because due to low melting point. Now, as we know that this is hypoeutectoid and this is hypereutectic. Sorry, hypoeutectic and hypereutectic. So liquid here, aluminum plus liquid, here silicon plus liquid. Now what happens here, when we cool this alloy, as we know there is no alpha and beta, so directly you will get aluminum plus eutectic mixture, that is aluminum plus silicon, and here silicon plus aluminum eutectic mixture. So we don't have here separate phase, so you will get aluminum matrix and eutectic of aluminum silicon. So silicon remains as it is, aluminum remains as it is. Let us see the microstructure. So this is the typical microstructure of an each unmodified aluminum silicon alloy. So this black black flecks are nothing but so unmodified silicon particles. So they are very dark, and the idiomorphic form of eutectic silicon diminishes the ductility of the alloy. So this is nothing but unmodified silicon eutectic. So this is the eutectic mixture of silicon, whereas these are nothing but unmodified silicon. So light gray color are unmodified silicon particles, and this is the black color is nothing but eutectic mixture. Now what happens here? It is due to this sharp. You can see. So this unmodified silicon eutectic is very sharp. It looks like needle, and it reduces the ductility. And this aluminum silicon alloy is becomes brittle. As we know, aluminum is ductile, but aluminum silicon, due to addition of silicon, it becomes brittle. It loses ductility. In order to overcome this situation, we will modify this alloy by adding certain modifying elements. And you can see, so this eutectic mixture is now converted into globules. You can see this eutectic mixture is now converted into globules due to addition of only 0.018% strontium. So this is fully modified silicon particles. They are very dark gray, and the fibrous form of eutectic silicon enhances the ductility of the alloy. So this is unmodified silicon aluminum silicon alloy, and this is modified silicon aluminum silicon alloy. Remember that due to modification, ductility and toughness enhances, but due to sharp nature or this idiomorphic form of eutectic silicon influences the ductility of the alloy, and ductility decreases and becomes brittle. So it needs to be modified by addition of boron, sodium, strontium. These are some modifying elements. You can add that, and it becomes globule. You can see it becomes globule, and automatically ductility of the aluminum silicon alloy gets improved. So aluminum silicon alloy needs to be modified. If you are using aluminum silicon alloy without modification, so chances are there that it may lose the ductility. So remember that points to be noted here is that aluminum silicon system is zero solid solubility system, where there is no solid solutions present. Aluminum plus eutectic mixture and silicon plus eutectic mixture you may get depending upon the chemical composition. And widely used alloys in casting industry are the eutectic alloys, particularly 12.5% silicon is the widely used aluminum silicon alloy in casting industry. It is due to fact that low melting point. Okay, so in case of automobiles, most of the components are manufactured in the aluminum silicon alloy. For example, your piston, which is used in IC engine, which is the best example of an aluminum silicon alloy, which contains 12.5% silicon and some percentage of other elements. So then crankcase is also best example of aluminum silicon alloy. Then radiators, top and bottom cover of the radiators, again aluminum silicon alloy. So most of the pneumatic pistons again manufactured by using aluminum silicon alloy. So there are a number of examples where aluminum silicon copper alloys are widely used. Again, in case of aerospace industry, aluminum lithium alloys are widely used because light elements, one of the lightest element present in periodic table is lithium, and density of aluminum is 2.7 gram per cc. When we add 1% of lithium into the aluminum, so overall matrix density decreases by 3%. That is due to addition of lithium. Remember that 1% addition of lithium decreases the overall matrix density by 3%. So that's why the aluminum lithium alloys are costlier but widely used in aerospace industries, where density is of prime concern.